All right, let's take a journey. Today, we're going to shrink ourselves down, way, way down, past anything you could see, to explore the incredibly strange quantum rules that literally build our reality. We're going to start with just a single particle of light and ride it all the way into the very heart of the atom itself.
So, here's the plan. First, we'll uncover a pretty mind-blowing secret that light was hiding in plain sight. Then, we'll see how that one discovery forced us to completely rewrite the rulebook for how atoms work. After that, we're diving deep into the nucleus to figure out radioactivity, and we'll wrap it all up by meeting the strongest force in the entire universe, the cosmic superglue holding everything together.
So first up, light's particle secret. For centuries, everyone figured light was a wave. Seemed obvious, right? Simple. But then, around the turn of the 20th century, a few key experiments started showing some weird cracks in that theory, hinting that something much stranger was afoot. And this all led scientists to a really, really big question, one that would completely change physics as we know it. Is light a wave, a particle, or somehow could it be both? The answer to this is what kicked off the entire quantum revolution.
And the key to unlocking that whole mystery is this thing right here, the photon. The evidence started piling up that light energy doesn't flow like a continuous wave. Instead, it arrives in these tiny individual packets, or quanta. So it's less like a smooth ramp of energy and more like a set of stairs. You get one whole packet or nothing.
And this is how they proved it. It's an experiment called the photoelectric effect. All you do is shine a light on a piece of metal. Now, if that light has enough energy, it literally knocks electrons right off the surface, and those moving electrons create a current you can measure. Sounds simple enough, but the results were, they were not what anyone expected.
See, here was the big puzzle. If light was just a wave, you'd think that a brighter light, a more intense wave, would give the electrons more of a kick and make them fly off faster. Makes sense, right? But nope, that's not what happened. A brighter light just knocked more electrons loose. If you wanted to make the electrons fly off faster, you had to change the light's frequency. You had to make it bluer. Weird. This whole thing led to an absolutely crucial insight, and it's all wrapped up in this little formula. It shows that the energy of one of those ejected electrons depends only on the frequency of the light particle that hits it. The brightness doesn't matter for the energy of a single electron. This was the smoking gun. Light really does act like a particle, delivering its energy in one single concentrated punch. Okay, so if light energy comes in these little packets, what does that mean for the atoms that are constantly absorbing and spitting them out? Well, this is where we get to the atom's own set of very strange rules. And this brings us to one of the biggest ideas in all of physics, quantization. It's just a fancy word for the rule that some things can only exist in specific set amounts. Think about a ladder, right? You can stand on the first rung or the second rung, but you can't just float somewhere in between. It turns out that energy inside an atom works exactly the same way. This idea led a physicist named Niels Bohr to come up with a totally radical new model for the atom. He said, okay, what if electrons can only exist in these fixed orbits, kind of like planets locked into specific paths? And he said, while they're in those orbits, they don't lose any energy, which totally broke the old rules of physics. To jump between orbits, an electron has to absorb or spit out a single photon with the exact right amount of energy. So that atomic ladder is really the key thing to remember here. Electrons are locked onto these energy rungs. They can't just be anywhere they want. And this quantization, this weird ladder-like structure, is the very thing that makes atoms stable. Seriously, without it, every electron would just spiral into the nucleus in a fraction of a second, and you, me, and the entire universe just wouldn't exist. All right, let's zoom in again. We've got the rules for the electrons sorted out, but what's going on in the very, very center of the atom? Let's dive deep inside the nucleus and talk about radioactivity. Radioactivity is basically what happens when an unstable atomic nucleus just falls apart. It spits out some radiation to try and become more stable. And what's wild is that it turns out every single element heavier than bismuth, that's element number 83, is fundamentally unstable. For them, it's not a question of if they'll decay, it's just a question of when. And that when is governed by this incredibly consistent, predictable rule called half-life. It's simply the amount of time it takes for exactly half of the radioactive atoms in any given sample to decay. It's a shockingly reliable atomic clock. So let's just walk through it. Imagine we start the clock right now at time 0 with a sample that is 100% full of these radioactive nuclei.
We wait for exactly one half-life to pass, and boom, 50% of those original atoms are gone. They've decayed and turned into something else. Now, if we wait for another half-life, half of what's left will decay. So now we're down to just 25% of what we started with. It's this perfectly predictable, exponential decay that makes it such an amazing tool for dating everything from rocks to ancient artifacts.
Okay, this brings us to our final stop, the deepest level of all. You've got this tiny little nucleus, right? And it's packed full of protons that are all positively charged. They should be repelling each other with an insane amount of force. So how in the world does it not just fly apart? Well, let's meet the universe's strongest force.
This is the strong nuclear force, and its properties are just mind-boggling. I mean, first of all, it's the strongest force in nature, period. It pulls on protons and neutrons equally. It doesn't care about charge at all. But here's the most important part. It's got an incredibly short range. It basically only works inside the nucleus. Take one step outside, just a millionth of a billionth of a meter away, and it's like it's not even there. It just vanishes.
But here, this is where it gets really, really weird. When you build a nucleus, something bizarre happens. If you take the mass of all the individual protons and neutrons you started with and add them up, and then you weigh the final nucleus you built, the nucleus is always lighter. It's like some of the mass just disappeared. This is what we call the mass defect.
So where did that mass go? Well, it was converted directly into energy, just like Einstein's famous E=mc² predicted. That missing mass wasn't lost at all. It became the enormous amount of energy, the binding energy, that holds that nucleus together against those incredible repulsive forces. The very glue of the universe is literally forged from mass being converted into energy. And what that all boils down to is this: the binding energy per nucleon. Basically, how tightly each particle is held in that nucleus is the ultimate measure of how stable an atom is. The more energy you have packed in there, the more stable that nucleus is going to be.
And that leaves us with one last, pretty powerful thought. We've gone from a single photon all the way down to discovering that a tiny bit of missing mass is what creates the stable atoms that make up our entire world. So, what happens if we figure out how to reverse that process? What happens when we take a stable atom and we force it to give that immense binding energy back? Well, that is the secret and the incredible power hidden at the very heart of the atom.